In this video, I want to give you a super easy and very intuitive explanation of decision tree classifiers. Decision trees are one of the most popular machine learning algorithms out there. If I have to look back in my 10 plus years of machine learning experience, I can tell you without any doubt that the machine learning models I used most of the times were tree-based models, usually decision trees or their advanced versions like XGBoost, gradient boosting trees, etc. One of the reasons these models are so popular is that they are very flexible to use. One, they can use any kind of data without much pre-processing, which means that the input variables don't necessarily have to be fully independent, and they are very good at capturing even the non-linear patterns in your data, which means that you can pretty much pass on all the input variables which you think could be useful into the model, and the trees are very good at determining which factors are useful and which are not. Another superpower of these decision trees is that you can graphically look at the finally trained model output tree and then see that how the model is doing the reasoning just like a human does. Most of the tutorials on decision trees I've found are very technical and math heavy. In this video, I'll try my best to make it very light on math and very heavy on intuition so you can easily understand how a decision tree is built and how the models are trained on it. As I said, decision trees mimic the human decision-making logic, which is also sort of tree-based. For example, if I want to know what to wear and I have to make a decision on that, it will go like this. Am I going outside or am I going to stay at home? Then am I going to a formal function or I'm just going to a grocery shop so I can wear something casual? And even on top of that, there could be factors like what is the temperature out there, and based on that, what I should be wearing, or what time of the day it is. If it is a day event, I'll be wearing something different. And if it is a night event, I'll be wearing something different. So if you look closely, you'd realize that the human decision making is actually a decision tree based logic. And same is the way we tell computers what to do. If you look at any code, it is based on if conditions. If this, then do this. If this, then do this. It is basically a tree-based model of making a decision. Now, to explain this concept, let's look at the Titanic dataset. I'm assuming all of you are aware of the 1913's tragedy of Titanic, where a lot of people unfortunately lost their lives. The reason I'm using Titanic dataset here, that it is one of the most popular machine learning toy dataset out there. Though the actual dataset out there has many features, for the simplicity of my example, I'll just pick about dozen rows and just 3 columns to illustrate my point on how a decision tree model actually works. So for this example, I'll just be looking at factors of what is the gender of the person who was in the Titanic, what was the class of the cabin they were traveling in. Because one thing we observed from the data is that people who were in the elite cabin survived much more than the people who were in regular cabin. And the third thing we'll look at is that were they traveling with family, which means that they have some children or some dependents with them or not. And based on that, we'll try to see that if they survived or not. So now let's look at this data set and then let's see that how an actual decision tree model works and make decision and get trained on this data. Now there are many versions of decision tree algorithms out there. The one I'm going to use in this example, it is the one which is the most popular. It is called ID3, and ID3 decision tree classifier is always a binary tree. That means that every stage it takes a feature and then it looks at what rows have class value of this versus the other and then keep dividing. Let's see what it looks like for this Titanic dataset. So this is here just under a dozen example rows from the Titanic dataset. You can see that we have columns of gender, cabin type, if they're traveling with family or not, and then whether they survived or not. And then we have people who are either female or male. Their cabin type is either regular or it is elite. And some of them are traveling with family or not. And then at the end, we see that how many of those actually survived and how many did not. So when we talk about binary decision trees, at every stage, we take a feature. So for example, it is feature 1, and then we divide it based on values 1 and then value 2. And then we take feature 2, and then at every stage we pick another feature and then another picture, and then we keep dividing. That is why when you look at the Python or any other code implementation of these decision trees, you'll see that the code is very highly recursive in nature, because if you, for example, if this is a tree and you look at it in a standalone way, you can see that this is a separate tree under this bigger tree. Okay, so enough of theory. Let me explain how a decision tree will be built on this data set, and I hope that along the way you will build the intuition for it. So the very first thing which we have to figure out is that what should be this root node from which the entire tree starts building. Now at every stage we want to create a root node which has the most prediction power to predict this output class. Now, to understand which of these features among gender, cabin type, and family has the most prediction power, let's look at this. So we can see that when we look at gender, we can see that 3 of them survived. For males, 3 of them survived, 2 did not. Female, 2 survived, 3 did not. And when we look at cabin type, we see this distribution: 1 survived, 4 did not for regular. And for elite, 3 survived, 1 did not. So we can clearly see that cabin type has more prediction power than gender, which sort of seems mixed. And then when we look at family, we can see that again, people who were traveling with family, they survived in 1 case and did not survive in 3 cases. And who were not traveling with family survived in 4 cases and did not survive in 2 cases. Now we want to know which of these features between gender, cabin type, and family had the most power in terms of separating this class of survived or not survived. And the way we mathematically calculate it is called entropy. And entropy is basically a measure of impurity of the classes for each of the variable. For example, when we separate based on gender, we see that the output is very much impure. It is 3-2 and 2-3 among survived and unsurvived. When we look at cabin type and divide it between regular and elite, we can see that the output is slightly less impure. So the purity level is high. And then when we look at the family type, we can see that it is also slightly better and less impure. So when entropy is basically impurity and we want to decrease it. Now there is a mathematical formula to calculate entropy, but I want to explain to you what the intuition behind this is. The value of the entropy, it varies between 0 and 1. 0 basically means only one class is present, which means the impurity in the data is 0. When it is 1, it means half and half, which means that the impurity in the data is maximum. And usually for other cases, it is between 0 and 1. And what we do is that every time we split the branch, now among all these candidate variables, we'll pick the variable which has the least amount of entropy. Now there are some online calculators which you can use to calculate the entropy, but when I calculate the entropy for this case, the winning candidate was cabin type. But because even as you can intuitively see that when we split the data based on the cabin type, we can see that we get a very clear class separation. We can see that people who are in regular are more likely not to survive than people who are in elite cabins, which are much more likely to survive. So because of this, the root feature for our decision tree will be cabin type. And then as it is a binary tree, it can take 2 values. One value is if the cabin type is regular, and the other is that if it is elite. Now in these nodes, we'll be looking at a subset of the data. At this stage, on the left side, we'll just be looking at the data where the cabin type is regular, and on the right side, we'll just be looking at the data where the cabin type is elite. So this is what the data looks like on the left side, and this is what the data looks like on the right side. You can see that for this data here, the cabin value is regular for all the rows, and on here, the cabin type value is elite for all the rows here. Now again, we come to another decision, that what feature should we use to again split the data here and here. Now since we have already used cabin type, so this is out of the question. We have to either use gender or we have to use with family. We'll again do the same calculation of calculating the entropy for gender and then for family here, as well as on the right side, and determine that which one has the least amount of entropy, and then we'll use that to make the further split. So let's look at the data here when the cabin type is regular. We can see that when we divide the data based on gender between male and female, male survived almost on equal basis. So we can see that the value here, when it is half and half, it is 0.5. And if it is totally separate class, that if only one class exists, in the case of female, we know that the value is 0. Again here, the value is 0 of entropy. This is not half and half, so it should be 1. So it should be somewhere between 0 and 1. Let's say it is 0.5. Now, when we sum up both of these, we can see that for gender, the entropy is 1, and for with family feature, the entropy is 0.5. So with family is the winner here. So here we'll use the feature with family. Now let's look at the data on the right side. All of them had elite cabin. That is what this branch is. Cabin type we have already used, so let me exclude this. Now we have to see which has the low amount of entropy between gender and with family. And when I look at the distribution of it, if I divide the data based on gender between male and female, I can see that this thing has an entropy, let's say 0.5. This thing has maximum entropy of 1. This is half and half, so it is 1. And this is full class separation, so entropy here would be 0. Now when we sum it up, we can say for gender it is 1.5. And with family it is 1.0. Now if we pick a feature which has the minimum amount of entropy, we should be again picking with family here. Now again the answer here is with family, but it's not necessary. It could have been different. And since I have picked with family here, just for this example's case, let me pick gender here to see that what the decision tree would look like. Okay. So now we have the data here. As we know, for with family feature, there are two potential outputs. If they are yes, they are traveling with family, and no, they are not traveling with family. And same is the case with gender, if they are male or if they are female. So now at each of these, we again have to make a decision based on which feature we have to use. So now when we look at this data, wherever the class separation is maximum, for example, when the person is female, we can see that they survived in pretty much every class. So we do not have to further divide this tree because pretty much everyone in this class survived. So here we will not divide this tree anymore. We can say that this is the final node, which is also called leaf node. And everyone here will be predicted as survived. And same story is true on the left side as well. We can see that when we split on the with family feature, anyone who was traveling with family pretty much did not survive. So here again, we can say that this node does not have to be divided again, and everyone in this did not unfortunately survive. But since these had some impurity, we are going to again split these two. So let's see what the data looks like for these two cases. So here the data look like this, here the data look like this, and here the data look like this. So here, since we have already used cabin type and family features, the only feature which we can split on is that of gender, because that is the only feature left. And here, since we have used gender and since we have used cabin type, the only feature left is if they are traveling with family or not. And the possible values here is, let's say, male, female, and here it is yes or no. So in this case, as we can see, when they are traveling with family, which is this value is yes, they never survived. So our final answer would be not survive. And in the case when they are not traveling with family, which is these two cases, they survived in both cases. So our final output would be. And in this case, we can see if it is female, there's just one data, they did not survive. And in this case, even if they are male, there's just one data which they did not survive. Using all this, we can see that we have built an entire tree which we can use to make a prediction about any future person if we want to know if they are going to survive or not. For example, if we want to know someone who is in elite cabin is female and not with family, if they're going to survive or not, we will first look at this. We'll come here on this branch. Then we'll say since it is female, they'll go to this branch, and then we can say that they are going to survive. I hope this explanation was easy to understand and easy to follow. Now a question might arise in your mind that here we were looking at only variables which had two potential output, which is either it is an elite cabin or a regular cabin, or it is female or it is male. What about if there are cases when there are more than 3 possible classes? The answer to that is very simple. Again, since we have to make a binary decision tree, which could just have 2 branches, even if there are 3 possible classes like A, B, and C, we'll pick any one of these classes, for example A, as the right branch, and the remaining of the classes, for example B, C, as the left branch. For example, if this is the feature and it has 3 possible values, A, B, and C, we have to make 2 branches. So let's say this would be A and then this would be B and C. Now the other question is, what if the input feature is a continuous variable? For example, the age of the person who is traveling in the Titanic. Because in that case, we take every possible value as sort of a splitting point and then see which one offers us a least amount of entropy. So the total number of calculations to calculate the best feature are much more. For example, let's take 2 scenarios. One, we just have 2 features and both have classes A and B, and this one has, let's say, C and D. So A and B are 2 possible classes for feature 1 and C and D are 2 possible classes for feature 2. So first we'll see what is the entropy of A and then entropy of B, and which one has the least amount. We'll just pick that, and we'll do the same exercise for C and D, and we are done. Let's say if there is another scenario where we have 2 features and feature 1, just like here, has 2 values, possible values A and B. We'll look at entropy of A and then entropy of B, and then we'll pick the minimum. And let's say if feature 2 is a continuous variable, and let's say its values are between 1 and 100, then we have to calculate the entropy for 1, then entropy if we want to split the data on 2, and then for 3, and so on till 100. Now, since computationally this is very ineffective, so the way we do it is that we order the data based on this variable. For example, if the values we see are 7, 13, 29, and 41, then between each of these, we'll take what is the middle number between these, and we pick 1 as a threshold. And then what is the middle number between these 2, and then we pick that as a threshold. And then what is the middle number between these 2, and then we pick the threshold. And we just calculate the entropy for these middle numbers and see which one gives us the least amount of value. Now, as you can tell, that the calculation for this could become very complex, especially once you have hundreds of features and millions of data points. The good thing is that we do now have help of computers which can help us train a decision tree classifier with just a bunch of commands. Let me show you how easy it looks like when you're using a machine learning library like scikit-learn to not only train a decision tree classifier, but also make predictions based on that. So with this single command of decision tree classifier, you can initialize a decision tree classifier, and then you can pass on the input variables as well as the output variable to train it with this just one single command. Once the model is trained, you can make the prediction based on any future dataset with just using this predict command, and you can even evaluate the performance of the model by passing on these test variables and the test output variable. Now, one thing I want to highlight is that though decision tree classifiers are very powerful, one thing they are prone of is that of overfitting. Going back to the example of the decision tree which we created for our Titanic dataset, we can see that as the decision trees become longer and longer, they train very well to the training dataset, which sometimes mean that they lose the general patterns which are hidden in the data. Now, there are a bunch of ways in which you can try to minimize this overfitting. One is that you train it with a vast amount of data so that they are trained on so much data that their chances of overfitting on the data are minimal. Most of the libraries have a parameter where you can define that what should be the height of this tree. So don't let this tree become too long, otherwise your tree would be overfitting to the data it has seen, which is the trained data. So a good practice is that you restrict the height or the maximum depth of this tree so that it generalizes on the data much more. Now, the other option which you can use to minimize the chances of overfitting is that if you let it train by default, it will grow, the tree will just keep growing until it has all the leaves with just one class. and that in a lot of cases mean, for example here, with just one row. So in the decision tree classifier libraries, you'll see there is a feature which asks for what are the minimum number of samples needed to make the further split. Now, if it is 1, the model in this case will come and create these branches, but if it is 3, since it needs to have at least 3 samples to go beyond, it will restrict here and these further branches will not be created. And the final, probably the most recommended option, that you use some ensemble trees. Random tree classifiers, XGBoost, and gradient boosting trees are all examples of such ensemble trees. I'll be covering this in another video of this series. One very important part of this discussion, which is how do we evaluate the performance of this decision tree classifier, is not covered in this video. I've created another video on this topic. The link for that should be somewhere here. Please check it out. Also, if you like this video and want to see more content like this, where I'm explaining in a very intuitive way different machine learning algorithms, please let me know in the comments below. Thank you so much for watching.